Good morning to all, and myself I am R. Hemalatha. I am working as Assistant Professor in Department of Mathematics at the Institute of Science and Technology, Puttur. Today I am going to discuss about the topic relations and algebraic structures. Here you can observe that we are taking the two sets, that is set A and set B. The set means the group of elements is called a set, and we are taking the binary operation, that is binary relations, as the addition or multiplication. Like that we can take any binary relation. Here we are taking the two sets, that is the set A and the set B, and we are forming a relation between the set A and set B. And by the definition, a binary relation from set A to set B is the subset of the Cartesian product of A cross B. Here you can observe that the Cartesian product A cross B is a subset of the binary relation between set A and set B. And we are taking the example as the set A contains the elements 0, 1, 2, and the set B contains the element A, B. We are forming a relation between the set A and set B. That means we are forming the relation between the elements in set A and the elements in the set B. You can observe that the relation R is equals to set of, that is we are forming a relation from 0 to the element A, that is the ordered pair of 0, A, and we are forming the relation between 0 to the element in the set B, that is 0, B, and we are forming the relation between 1 and A, that is 1, A ordered pair of, and the relation between 2 and B is the ordered pair of 2, like that we are forming the relations. Relations and their properties. Here we can observe that the Cartesian product of the set A cross A is the subset of the set A, and we can observe that here we are taking the relation A is equal, that is set A is equals to the elements 1, 2, 3, 4, that is the set A contains the 4 elements 1, 2, 3, 4, and we are forming the relation between them, that is R is equals to the ordered pair of 1, 1, that is the relation between the same elements, that is 1, 1, and that is like 2, 2, 3, 3, 4, 4, like that. When we are forming the relation between the other elements like 1, 2, 2, 1, 3, 4, 4, 3, 4, 1, like that we can form the relation. The relations are of three types, that is reflexive relation, symmetric relation, and transitive relation. For the symmetric, anti-symmetric also is there. Hence, we are going for the reflexive relation. Reflexive relation means we are taking one element, that is the set A contains some elements. In that, I am choosing a element, that is small a belongs to capital A. Here, the meaning is the small a is contained in the set A. The relation between the same element is called the reflexive relation. Hence, we are taking B belongs to B means then B, B belongs to R is the reflexive relation, because we are forming the relation between the same element is called the reflexive relation. For example, in the set A is equals to set of 1, 2, 3, 4, we can observe that here the relation between the same elements are 1, 1, 2, 2, 3, 3, 4, 4 all comes under the reflexive relation. Next one is the symmetric relation. Hence, we are taking the set sum A is equals to set of A, B, C, and so on. Here we are taking the two elements, that is A, B, and the relation between the two elements A, B, that is mentioned by A, B belongs to R, which tends to the B, A belongs to R. That means here you can observe that here 1, 2 has the relation, means that 2, 1 also having some relation. That type of relation is called the symmetric relation. Next one is the anti-symmetric relation. Anti-symmetric relation means there is a relation between A and B elements, and here the symbol, cap symbol denotes the and. Then B, A also belongs to R means then A, B has some relation and B, A has some relation means then it tends to A is equals to B, that is A and B are elements of the same elements. This type of property is called the anti-symmetric relation. Next one is a symmetric transitive relation. Here you can observe that the two elements are A, B belongs to R means hence we are taking a set A is equals to there is some elements A, B, C and D are like that. Here A, B elements has the relation and B, C has the relation means which tends to the relation between A to C. That relation type is called the transitive relation. For example, you can take A is equals to the set 1, 2, 3, 4 and you can observe that here there is a relation between 1 to 1 and the relation between 1 to 2, then it has the relation between 1 to 2 is called the transitive relation. If there is a relation between AB and BC, then it tends to the again relation between A and C is called the transitive relation. Next, going to the functions, hence we are taking here two sets, that is the one set, the first set is called the domain and the second set is called the range. Here in the domain we are taking the set, that is the elements in the set is called the domain, and the images of the domain elements is taken in the range, and we are forming a relation between is called the function. By the definition you can observe that a function is a relation in which each element of the domain is paired with exactly one element of the range. That is, every element has an image that is here mentioned by is paired with exactly one element of the range. Another way it is saying that in the computer modulation we can say that each input has the one and only output. That is extends, that is here the relation between x and y is, here x has the image y and the relation between them is taken as the f of x is equals to y. Group theory, hence going to the group theory, it is a part of the algebra which is useful for the further studies. We are going for the algebraic system. If you want to study the algebraic system, means we have to take a set. That set contains some element, that is a non-empty set, because by empty set we gone to anything. That's why we are taking a non-empty set. By that is some elements are there. By using that elements, we have to prove the properties for the algebra. To prove the algebraic system, we have to prove the closure property. To prove the semi-groups, we have to prove the two properties. For the monoids, we have to prove the three properties. For the groups, we have to prove four properties, and for the abelian groups or commutative group we have to prove the five properties. First you can go for the algebraic system. We have to prove only the closure property. Closure property, that is if they are taking the two elements in the set, then the relation between these sets also belongs to S only. That property is called the closure property. Here you can observe that A comma B belongs to S means A circle B also belongs to S. That property is called the closure property. If it is exists means that set is called the algebraic structure. Further going to the semi group, you can observe that by satisfying the two conditions, that is the closure property and associative property, then the set is called the semi group. Here closure property means the relation between the two elements is also belongs to the same set is called the closure property. Associative property means here we are taking the three elements in the set S, that is A comma B comma C belongs to S. Then the relation between them, that is A related to B, that relation to C is equals to B related to C and related to A is equals. That is, for example, if the binary operation is the multiplication, then we can taken as A into B into C is equals to A into BC is taken as the associative property. Hence, we are going to the monoid. Monoid means it has to a set has to satisfy the three properties, that is the closure, associative, and identity properties is called the monoid. And also we can take another definition as a semi group which satisfies the identity property also is called the monoid. Here in the identity property we have to take the identity element. We have to identify the identity element, that is taken as the small e. Here as for the circle operation we don't mention any identity element. By based on the problems only it can be taken as the identity element. But for the multiplication, one is the identity element, because A into 1 is equals to 1 into A is equals to A. That's why for the multiplication, one is the identity element. And for the addition, we are taking the identity element as 0. That is A plus 0 is equals to 0 plus A is equals to A. By satisfying these three properties, that is closure, associative, identity element, then the set is called a monoid. Next, going to the group, if a set is said to be a group, then it has to satisfy the four properties. That is, first one is closure, second one is associative, third one is identity, and fourth one is the inverse properties. You can observe that another definition also is that a monoid which has the inverse property is called a group, or a semi group which satisfies the identity property and inverse property is called a group. Here the inverse property means here we have to take the element, that is A comma A belongs to S means then A inverse also we have to belongs to S. If multiplication is the binary operation means A belongs to S means then A inverse also belongs to S, then A into A inverse is equals to E, that is the identity element 1. That type of property is called the inverse property. If the set A satisfies the closure, associative, identity, and inverse properties is called a group. Next, going to the abelian group. The group which satisfies the commutative property is also called an abelian group. For example, the commutative property means if A comma B are the elements in a set S, then A into B is equals to B into A. The property is called a commutative property. Along with these four properties, commutative properties also exist. Then the property is called abelian group, or it has another name, that is the commutative group. Cyclic group. Cyclic group means if you are taking a group, some G is equals to set of A comma B comma C and D and so on. If that set, that is, a group is formed by a single element. A single element, for example, we are taken here a cyclic group, always abelian group, but not every cyclic group is a cyclic group. Here we can observe that small a is a belongs to G, then every element should be formed by the small a only. That is, some G is equal set of a power 0, a power 1, a square, a cubed and so on. That type of set is called the set is belongs to the group is called a cyclic group. A group which has the elements which is produced by the single element is called a cyclic group. From coming to the subgroups, here we can observe that a set G has A, B, C, D and so on some elements, and also another set H is equals to some elements A, B. Here I can observe that H is a subset of G. That is, the elements in the set H contains in the element set G. G also a group, and H itself is a group, is called a subgroup. That means H should be a subset of G, and H itself is a group. Then it is called a subgroup. Coming to the homomorphism and isomorphism, here you can observe that here we are taking the domain G, that is having the set G with the binary operation star, and taking the range, that is G dash with the binary operation plus circle, and we are forming a relation between G and G dash. That is we are taking the set G and set G dash and forming a relation between the G and G dash is called the function f. Then the function is defined by f of the elements in G, that is A, and the binary operation is star, that is A star B is equals to the elements in G dash in the form of f of A, f of B, f of C, like that. Here A has the image of f of A and B has the image, that is f of B, and here the binary operation is plus circle, that is f of A star B is equals to f of A plus circle f of A. This type of relation is called a homomorphism. Isomorphism means there is a function between G and G dash. If these functions are said to be isomorphism, means it has to satisfy the three properties, that is one-one relation, onto relation, and also homomorphism. One-to-one relation means the element in G has exactly one image in the G dash, and onto means f of x is equals to y, that is f of A, that is if any element in the G is x, then element in the y, G dash is y, then the image of the x, that is f of x is equals to y, satisfies, means it is called onto, and there is a relation between two elements, that is f of A star B is equals to f of A plus circle f of B, like that we are taking means homomorphism. If this the set satisfies the three property, that is one onto, and so homomorphism is called isomorphism. You can take the example here, that is f of A plus B is equals to, here we are taking the elements of a function as f of x is equals to 2 power x, x belongs to R, here R is the relation, that is the positive real numbers we are taking. In the place of x we are taking here A plus B, that is f of A plus B is equal to 2 power A plus B. By using the formula A power m plus n is equals to A power m into A power n, here we are taking 2 power A into 2 power B, and this 2 power A is mentioned by f of A, and 2 power B is taken as the function f of B. Here you can observe that f of A plus B is equals to f of A into f of B. This is the perfect example for the homomorphism.